Biologically, sexual satiation is a dead stop. It is a sudden, aggressive shutdown enforced by a specific neurochemical failsafe. We casually refer to oxytocin as the love hormone, as if it flows freely the moment we feel close to someone. In reality, its release is governed by rigid, highly predictable endocrine feedback loops. Under standard conditions, the post-orgasmic state for both males and females is bound by strict biological markers that actively prevent further arousal. The primary enforcer of this biological lockout is prolactin. When it floods the system after climax, it acts as a chemical kill switch to signal immediate satiety. You can manipulate these loops through a structured, multi-round behavioral protocol. By combining deliberate temporal delays with extended tactile stimulation, you can heavily optimize the brain's paraventricular nucleus, massively increasing its capacity to release oxytocin. The true neurochemical shift occurs when you combine that specific temporal pacing with targeted pharmacokinetics. By introducing a microdose of a dopamine D2 receptor agonist, you intervene at the pituitary level to entirely bypass the biological refractory lockout. The biological refractory period operates as a specific, mappable chemical barrier, one that can be systematically dismantled. To dismantle that barrier, we first have to map the baseline mechanics of oxytocin. In the bloodstream, oxytocin has a remarkably short half-life, clearing out completely in just 3 to 5 minutes. Look at this split-screen visualization. On the left, we track a standard oxytocin curve. Taking a multi-hour break between rounds doesn't physically stack oxytocin in your plasma. Within 30 minutes of stopping, the hormone levels drop back down to absolute zero. On the right side, we track dopamine. When you engage in arousal but stop before climax, you create a neurochemical cliffhanger. Denying the brain its expected satiety triggers a sustained, escalating release of dopamine, the neurotransmitter of pursuit. This accumulated dopamine actively feeds the oxytocin-producing neurons in the hypothalamus. It continuously stimulates and primes that neural circuitry, building a massive reservoir of anticipation. One major physiological roadblock can ruin this entire priming process: the sympathetic nervous system. If either partner feels rushed, stressed, or vigilant, cortisol enters the bloodstream. Cortisol acts as a hard brake on this system, actively halting oxytocin synthesis. Engaging in multiple rounds of extended touch and grounding systematically drains the accumulated cortisol out of the body entirely. By the time you reach a third round hours later, baseline stress markers are effectively zero. With cortisol eradicated and dopamine highly elevated, the biological ceiling for oxytocin release is radically amplified. Structured, intermittent sexual pacing functions as a mechanical pump, utilizing dopamine to build intense neural anticipation for a massive oxytocin payload. When you execute the climax on the third round, the physiological event is a massive central dump of both oxytocin and prolactin. The endocrine system responds most powerfully to partner-based coitus, generating a prolactin spike up to 400% greater than what occurs solo. This diagram illustrates exactly how that massive prolactin surge forces the male and female endocrine landscapes to split into entirely diverging pathways. For a male, prolactin acts as a direct negative feedback regulator. It aggressively shuts down the accumulated dopamine pathways to enforce biological satiety. This sudden crash from a high dopamine ceiling results in a profoundly prolonged refractory period, inducing intense physical sedation. The female brain does not possess this absolute dopaminergic lockout mechanism. The prolactin spike still occurs, but dopamine pathways remain largely uninterrupted. The multi-hour delay induces extreme pelvic vasocongestion. This heavy, sustained blood flow leads to acute post-orgasmic clitoral hypersensitivity. Depending on individual physiology, this extreme neural sensitization creates either a highly accessible window for multi-peak orgasms or a deep, full-body somatic release driven by the sheer volume of central oxytocin. Both sexes receive the oxytocin amplification, but prolactin dictates the behavioral aftermath. It enforces a rigid narcotic crash in males, while leaving female pathways biologically sensitized. Removing prolactin from the equation requires a specific pharmacological intervention, a drug called Bromocriptine. Mechanistically, Bromocriptine is a potent dopamine D2 receptor agonist. This 3D visualization shows how these molecules target the anterior pituitary gland. They lock into D2 receptor slots to exert their primary clinical effect, the powerful suppression of prolactin secretion. With the drug active during the third round climax, the massive oxytocin dump still occurs, but the subsequent prolactin surge is completely blocked. For the male system, the impact is structural. Because prolactin cannot signal biological satiety, the physical refractory lockout is effectively bypassed. For both partners, the profound, heavy sedation that typically follows the massive, multi-hour buildup is now completely eliminated. This completely shifts the texture of the afterglow. Oxytocin remains fully bound to preserve emotional closeness, but the physical state shifts drastically. Without prolactin, the nervous system remains in an elevated state of alert wakefulness and hypercharged endurance. By artificially sustaining dopamine signaling, D2 agonism proves the post-sex crash is an entirely optional physiological state, rather than a mandatory limit of human energy. Attempting this protocol faces a major real-world hurdle. At standard doses, bromocriptine triggers severe alpha-adrenergic and gastrointestinal side effects, including acute nausea and sudden drops in blood pressure. These side effects cause the sympathetic nervous system to panic. Cortisol instantly spikes, destroying the oxytocin synthesis required to make the protocol work. The solution lies in a pharmacokinetic principle called threshold asymmetry, mapped out here on a 3-tiered activation scale. Different parts of your nervous system react to dopamine agonists at vastly different plasma concentrations. The D2 receptors on the pituitary lactotrophs are extraordinarily sensitive, requiring very little agonist presence to shut down hormone production. The higher tiers, like the trigger zone for nausea, require a much higher plasma concentration to trip the biological poison alarm. You exploit this by administering a subclinical microdose, roughly 1/4 milligram, alongside a small food buffer at the very beginning of round 1. Oral bromocriptine takes roughly 2.5 hours to reach peak concentration in the bloodstream. The absorption securely crosses the low pituitary threshold, but safely flattens out before ever touching the brainstem threshold. This precise timing allows the drug's maximal efficacy to align perfectly with the exact moment the natural prolactin dump attempts to occur during the climax of round 3. By exploiting the distinct sensitivity of the pituitary gland, we can mathematically separate the desired endocrine shutdown from the debilitating cortisol response. The human endocrine system is highly malleable, but it strictly obeys underlying biochemical logic. If we look at this comparative visualization of the 3 distinct waveform outcomes, the mechanics become completely transparent. The natural intermittent protocol trades temporal delay for an amplified central oxytocin payload. That natural amplification inevitably enforces deep prolactin-driven sedation. The pharmacological protocol severs the biological link between orgasm and prolactin. It achieves the same massive peak, but sustains a high-energy plateau instead of crashing. Manipulating receptor specificities transforms a fixed biological endpoint into a controllable variable. The entire texture of the post-climax state, whether it brings a somnolent melting or electrified endurance, rests entirely on the presence or absence of prolactin. None of this optimization is possible without the foundational requirement of suppressing cortisol and dismantling the amygdala's hypervigilance. Human sexual satiation is not a rigid biological boundary. It is a highly pliable neurochemical equation governed by anticipation, precise timing, and targeted receptor modulation.